Good evening, everyone. May I please know if I am audible? Can someone just put it in the chat box whether I'm audible or not? Am I audible to you people?
Yes, ma'am.
Oh, okay, thank you so much. Okay, so welcome to the first live session, the weekly live session for the course Geomorphic Processes, Landforms and Landscape. This is taught by instructor Professor Javed Malik. He's from the Earth Sciences Department in IIT Kanpur. And myself, Ananya Parthapradeep Mukherjee, I am a PMRF fellow doing my research in the Department of Earth Sciences in IIT Kanpur. So the perspective with which these live sessions will be taken is first of all a brief summary of the weekly content that is given to you on the NPTEL course, the platform, and you all are given assignments for every weekly content. So what will be done in these weekly sessions is we I am going to obviously summarize the entire thing, and the content that is going to be shown here and that we will be discussing during these sessions will be related to your assignments. And the content is going to help you solve the assignments. So most of the assignment questions are either conceptual based, or they will be in any numerical format. So I will be trying to cover all those topics that are mentioned in your assignments, so you all can refer to these lectures while attending. You can interact with me, you can get your doubts cleared from the content that is already given to you. And obviously any question regarding your assignment questions, if you have any doubt regarding them, you can ask them over here. And any query you have related to these online these live sessions, you can ask them in the discussion forum also. Recordings of these will be provided to you at a later date, but it's a suggestion and it's also a request from you people to please join in the live session, since the whole point of conducting these sessions is to have a live interaction. So unless and until people attend, the whole point of live session is a bit lost. So I request everybody who is over here right now, and if you can pass on the message to please attend these and try to get the most out of these lectures. In case I am unable to clear any doubt over here right now, please post them in the discussion forum, and I will get back to you after clarifying with the instructor or the official teaching assistant that is assigned for this course. So that was the brief introduction. So for the this course is actually a part of the earth sciences as a subject. What is earth science? Earth science is applying physical, chemical and biological and mathematical principles on earth as a whole. We try to understand the processes that are shaping the earth, that are constantly changing the different aspects of earth, and how they are directly related to us or indirectly related to us, how they cause how they are beneficial to us as well as hazardous to us. So geomorphic processes are the processes that change the landscape of the earth's surface. So you see mountains, you see rivers, you see drainage basins. These are some of the examples of some agents that are kind of creating these landforms, these features on the earth. So this entire course is we are going to learn about how these processes are behaving, how are they happening, and what are the results of these processes on earth. Okay. So again, introduction. Geomorphic processes, the study of these processes is actually called geomorphology. Okay. So geomorphology comes from the Greek words. Geo means earth, morph means shaping, and logy is the science. So how is the earth surface morphing into different features? That is the study of geomorphology. So one of the most prominent kind of branch of geomorphology would be your applied geomorphology, where we try to understand the relation of these processes with environmental geomorphology. Okay, now environmental geomorphology can have two influences or factors which are affecting, that is your natural processes and also the human processes, anthropogenic processes. We are going to learn these things in detail in in this in today's session as well as in the later on sessions. So that's what we said, that environmental geomorphology is a kind of an interaction between both natural and human influences. And we also have cultural landscapes. Cultural landscapes is you might have heard about archaeological areas or sites. They are also kind of affected by the past geomorphic processes. Maybe there might have been flooding, or there might have been an earthquake which kind of ended a civilization, or it affected the way the civilization that was established. It might have ruined it, or it might have changed the structure of some of the areas. So that would come under your cultural landscapes. So this is a brief course outline that you have for this course. So you will first understand the fundamentals of earth system, the surface of the earth, and the different processes that are happening on earth. Then you have the interior of the earth. We need to learn how the interior structure of the earth is represented, how, what are the processes that are happening within the earth, which kind of has an effect on how the earth processes or the earth surface processes also take place. And the major part of the those processes would be your plate tectonics and sea floor spreading. Then you have different systems that are constantly interacting with earth as a system. You have the atmosphere, then you have the hydrological cycle, and then you have how the energy is interacting with earth, how is earth kind of giving out the energy or absorbing the energy, and how are the climate and the weather that changes that we see on earth, how are they related to your hydrological cycle as well as your atmospheric system. So this is something that we will learn. Then there are different geomorphologies, branches of geomorphologies that are that we learn with respect to the natural agent that is causing them. So when we talk about fluvial geomorphology, it's the geomorphology, the landscapes that are formed due to the action of river. Then you have aeolian geomorphology, that is due to the action of wind. You have glacial, that is due to the action of glaciers. You have karst geomorphology, that is due to the presence of massive calcium carbonate rocks. We will also learn about some different kind of rocks that are kind of influencing geomorphology as a whole. Okay, and then you have coastal and submarine geomorphology. So this is the effect of your tides, your waves, and also submarine, as in at the kind of the shelf, continental shelf or close to the shore, and also marine bed, the ocean bed or sea bed that we talk about. We will talk about that geomorphology also. So this is your entire kind of outline of the course, that is geomorphic processes, landscapes and landforms. So we will now move on to some very basic facts. Whenever we start learning about the earth, we need to understand the time scale that the earth, the processes that happen on the earth. Okay, so since earth itself is kind of 4.5 billion years old, okay, approximately, you plus minus 50 million years. Okay, so you understand that earth in its on its own is so old. So the processes that have shaped the earth also happen at a time scale which is kind of not apparent to us as humans. So maybe as you know that Himalaya started forming around millions of years back. So it is still growing. Okay, so it's the centimeter growth that we see now, that is very, it is very less compared to the height that we see already. So the height that the Himalayas have reached already, that has happened over millions of years. Okay, so it is important for us to know the different the age, the not exact age but approximate age of the things that have formed on earth. So till now the oldest dating record that we have found is from Western Australia, that is 4.36 billion years. So zircon crystal is found in one of the rocks that is present, that is exposed in the area, and you date these rocks based on some radiogenic isotopes. Over here I have mentioned some of the common radioactive isotopes that we use to study the and date earth and the rocks on the earth, and we try to understand how long a certain landform or feature has taken to form on the earth. So you have potassium, rubidium, lanthanum, and then the most common one that we use is the uranium and the thorium one. So this is very commonly used for kind of dating the different kinds of rocks on the earth and other landforms that are present on the earth. So now we come to the basic concept of systems. What is a system? System is something where the elements of the system interact among with each other and also with other systems that are around the particular system. So when you say open system, that means both matter and energy is kind of taken and given out, and it's exchanged between the systems. Okay, uh, matter goes in, comes out, and also energy comes in and energy goes out. So as a human body is a good example of an open system. Then you have a closed system. Now in closed system the matter is not exchanged. Okay, so there is no exchange in the matter, it is only the exchange of energy. Okay, so like as a whole, earth is it's an example of a closed system. We do not see any earth material being thrown out into the space, but what we receive is the energy from the sun. We receive the energy from the sun and we also give it back to the space. Okay, so that's an example of a closed system. What's an isolated system? Neither matter nor energy is exchanged with the surrounding. So a thermos or vacuum sealed flask is an example of such a system. So now we know that earth itself is a closed system. Okay, but within the earth system there are a number of systems which are interacting among each other to make earth as a whole a closed system. Okay, so examples or the systems that are okay ma'am, is it okay, one thing, I'll just take up the questions in between. Okay, so like I do not end with the flow, and I'll just answer your question, Kuldeep, in a like once I reach a certain point, okay, of the session. Okay, so when we are talking about earth as a closed system, and there are a few systems in the earth itself which act as open systems. Okay, because of the interaction between these open systems, earth will function as a system where only energy is exchanged with the surrounding space. So examples of these open systems which are acting within earth system, you have atmosphere, you have hydrosphere, you have biosphere, and you have geosphere. Okay, Atmosphere is obviously the the kind of atmospheric layers that are surrounding the earth. Okay, every layer has a kind of a function with itself, and energy radiations that are coming in the earth has to pass through these atmospheric layers, then they reach the earth's surface. Then the earth also reflects back some of the energy through these atmospheric layers and back into the space. Okay, so you have the effect of the energy and going out, and also because the elemental, or you can say, what you have, the gases, the clouds, these are also interacting within the atmospheric layers. Okay, so we consider that as matter. So that's why atmosphere is an open system. Then you have hydrosphere. Hydrosphere consists of all the input and the output that is related with the water resources on earth. Okay, so you have glaciers that are melting, then forming into a river, and different kind of streams. Then these rivers and streams, they get obviously they go down to the ocean or the sea. Then you have the evaporation of the water from the streams, as well as the mostly from ocean and seas. Okay, so then this is again given, it's going back, forming the clouds, and again you have precipitation. With the precipitation, you are again recharging your streams and different water reservoirs, as well as your glaciers from forming snow and ice. Okay, so this again, there is an exchange of the energy and the matter in the hydrosphere. Okay, so that is again acting within the earth system. Then you have biosphere. We are a part of the biosphere, and most of all the living things are a part of the biosphere. So our interactions with the earth, our interactions with each other, our interactions with the other living beings, all of this forms a part of the biosphere. Okay, so biosphere is again an open system because we are exchanging energy as well as matter. Then you have geosphere. Geosphere is what we are going to be concerned about most when we are learning the geomorphological processes, and how the geosphere interacts with your hydrosphere and atmosphere and biosphere. Okay, so geomorphology is kind of you can see that it's the science behind understanding how the geosphere is interacting with the other spheres or the other systems. So in geosphere you have weathering and erosion of the rocks that we find on earth surfaces. Okay, then you have the metamorphic rocks that is formed due to the melting of igneous rocks and sedimentary rocks. Weathering and erosion of both igneous and metamorphic rocks is going to give you sediments. Sediments, when they are compacted under a lot of pressure, they will form into a rock on their own, that is the sedimentary rock. So this is also a cycle where your energy and matter is again interacting, again being exchanged from one part to the other, and your hydrosphere, your atmosphere and biosphere is also kind of interacting with the elements of the geosphere. So all these four systems are open systems, and together they form, like when they interact among themselves, they will form the earth system. Earth system is a closed system. So this is a basic concept, and how you kind of understand earth as a system. So I'll just go to the question that was asked. Ma'am, is it really needed to memorize these duration of decaying of radioactive isotopes? It's not necessary to memorize, but it would be easy if you remember the half life of these the radioactive isotopes. So it will be easier for you. Maybe you will be asked a numericals during the exam if it's relevant, but at least for the very often used radioactive isotopes, like you have uranium, thorium, and potassium, carbon. So these four, you can just remember the half life of these radioactive isotopes. Okay, so now we understood the different kind of the systems that are forming the earth. Now earth on its own, how does it look, and how is the surface of the earth formed, what is it composed of, how does it look, if you want to understand how earth looks inside. Okay, so that's when we study the interior of the earth. Now this layered structure that you see of the earth's interior, okay, this is a very pictographic representation, obviously, excuse me. So to understand this, studies have been carried out by using seismic waves. Okay, so seismic waves, when generated, they form into P wave and S wave. And suppose you have you know seismic wave is generated, suppose say here. Okay, so it will travel within the earth, okay, within the earth, and it will get either reflected from the different layers that are forming the earth's interior, or it will get or it will pass through them, or it will get reflected back from the discontinuities that are present. Okay, so this is a very brief introduction to how we study the earth's interior. This will be explained in the coming week's lecture also, and I'll also take it up in the live session. Okay, so just in brief, you have the inner core, okay, then you have the outer core, then you have the mantle, then you have the asthenosphere, and then you have the crust. Now, what is the lithosphere? Why is it important for us to understand lithosphere? Is because the lithosphere is where the geosphere is acting, okay, where the geosphere is interacting, and also the geomorphological processes that we are going to study in this course is actually acting only on this lithospheric layer. Okay, so asthenosphere is the upper part of the mantle, and the crust together, asthenosphere and crust together, will form your lithosphere. As you can see that asthenosphere is capable of flow. Because the asthenosphere is capable of flow, and because mantle is a convecting layer, as we will learn later on also, and it's a basic thing. So because of these convective flows and because of the asthenosphere's ability to flow, we see that the continents that are present right now, they can move away or towards each other. Okay, the basic principle that is giving rise to plate tectonics is because of this asthenospheric flow and also the mantle convection currents. Okay, so that is why, to understand how the earth's surface is shaping and being changed with time, we need to understand the plate tectonics, or how these plates are forming different features on the earth surface, sorry. Okay, so as I said that the mantle works as a convective cell. Okay, so the mantle material, it rises at one place, and then it sinks on the then it travels like horizontally below the crust, that is in the asthenospheric layer. Okay, then it will again go down, and then again it will rise. Okay, so there are these cells that are present within the mantle, which is driving the different continents, as we see here, the different continents away or towards each other. You can see that these triangles, these are actually places where the plates are moving towards each other. Okay, if they are moving towards each other, then they are a part of the subduction zone. Okay, and where you can see these dashed lines, okay, this is where your mid oceanic ridges are forming. This is where the plates are moving away from each other. Okay, this is a brief concept of the plate tectonics and how the mantle convection currents drive the different features, landforms that are forming on earth surfaces, like your mountains, then you have trenches, then sea floor ridges, mid oceanic ridges. These are formed due to the influence of plate tectonics. So now we understood the basic understanding of the earth first as a system, then the timeline that the earth the earth processes take. It's a huge timeline. Okay, and then we learned about the earth's interior and what is driving the changes, one of the factors that is driving the changes on the earth's surface. Okay, so now we come to geomorphology. As I have briefly told before, that geomorphology is the study of landforms and the processes that are shaping the earth's surface. Okay, so it's because of the interaction between the earth's tectonic framework as in the the presence of the plates and the tectonic processes that are kind of driving them away and towards each other, and the earth surface interaction with the atmosphere that is present, and also the biosphere that is present, and the hydrological, the water resources that are present. Okay, so uh, all the landforms are kind of formed due to the close interaction and close interrelationship between these factors. Okay, so geomorphological processes also have we it is essential to learn about them, because a lot of environmental issues and also what we call as natural hazards are a part of these geomorphic processes. Okay, so when you combine both the effects of natural processes and human activity, both together have to be considered to understand the geomorphic processes and their effects. So over here in the diagram you can see how you have climatic forces as well as tectonic forces which are driving the interactions between the biosphere, hydrosphere, atmosphere. Over here we also have cryosphere, and geosphere is kind of the aspect of the lithosphere over here. Okay, so all these spheres are interacting with each other due to the forces of climate. That in that you have your solar energy that is coming, you have the cosmic radiation, and the tectonic forces is this the as I talked before about the mantle upwelling and downwelling of magma, that is due to the presence of asthenosphere. Okay, so this is in a very nice concise gist of what exactly are we going to study when we are studying about geomorphology. This is the interaction between all the spheres. So one of the principles that we consider when we are studying about geomorphology is that during the earth's history, okay, whatever processes are happening right now in present, the same processes have taken place in the earth's past. Okay, so suppose we are talking about the flooding of a river. Okay, when the river floods, the the sediments, they are getting deposited farther away from the banks, from the the normal banks of the river. Okay, so we see this flooding and then again retreating, then flooding and then retreating. Because of the cyclic process, we can see that the drainage basin expands. Okay, when we see that this drainage basin is expanding, we can understand that this has happened even previously. That is why we see big drainage basins, like Ganga is one of the example. Okay, so it has a large drainage basin. That cannot happen just in like within 100 years. It has been happening from a long time back. Okay, so that is why we use a principle called principle of uniformitarianism. Okay, which suggests that the natural laws that are operating in the present day observations have always operated in the universe, and this will apply anywhere in the universe. One example is that you can see a picture of Grand Canyon over here. So obviously you can see the river is still flowing through the faces of the canyon. Okay, so this has not happened right now or in just past 50 years or 100 years. This must have taken a long time. But since the river is still flowing through these canyons, this means that this was happening even in the past, that the river was flowing like this even in the past. So, this is one of the principles that we use to understand the geomorphological features or landforms on the Earth's surface. So, these geomorphic processes, the processes which are shaping the land as we see, okay. So, there could be endogenic factors and exogenic factors. Endogenic factors are internal influences, okay, and exogenous is external. When we talk about endogenic or internal, we talk about mostly subsurface subsurface factors that are influencing, or maybe the driving forces for these processes is within the earth's subsurface, that is below the earth. Exogenic is whatever is happening on top of the earth, okay, on the earth's surfaces. So when we are considering endogenic, okay, so there are two kinds of movements that can happen, or considering the timeline of the processes, or like timeline of these processes, like how long would they take to show a kind of a result. So you have slow movements and you have sudden movements. So when you talk about sudden movements, okay, volcanic eruption is a sudden movement. Obviously, the build-up beneath a volcano will take a long time. Okay, so the build-up, the magma chamber being filled by the mantle material, that is going to take up a long time. But when the volcanic eruption takes place, it's a sudden change in the land around it. So you will have lava flows, which is considering the earth's time, it is going to be a quick change in the surroundings. So anything, the ash cloud that has been that is given out, that is going to settle faster, and it will change the way that region looks in a very quick it in a quick time period. Similarly, earthquakes, when they happen, they can change the way the region is set up, the region, the kind of the rest position of the region. It gets disrupted very fast when you have earthquakes. Okay, so these are sudden movements. Obviously, as I mentioned before, the build up of these movements will take a long time, but when they do happen, the changes that we see on the earth's surface is going to be sudden and quick. That is why this is considered as sudden movements, but their driving forces are again endogenic, because of the processes that are happening below the earth's surface. When then you go to slow movements, as in these surface these processes are changing these earth surface, like in a long time period. The, as I said, mountain building over here, when we talk about orogenic processes or mountain building processes, these are happening, we can see, but the rate of them, the rate at which they are happening is very slow. Okay, so we can see the the great heights of the mountain peaks, and they are also increasing every year, but the rate is very slow. And when you talk about epiorogenic, that is continental building, okay, that again could be, say, suppose you are having a depression, okay, the depression is increasing day by day, okay, or a plateau region is also increasing day by day, or somewhere in that sense, when you talk about continental building, that is also a slow process. And the again, the driving forces of these epiorogenic and orogenic processes is going to be endogenic, that is, it is happening within the earth's surface. Okay, now when we talk about mountain building, there are two kinds of forces that are causing them. Okay, One of them which we know very well, Himalaya is an great example of this, that is your compression. We know that that happened because the Indian plate and the Eurasian plate, they collided, okay, and due to their collision, at the margin, the the rocks, the sediments that were present, and also the sediments that were a part of the Tethys Ocean, okay, the ocean closed due to this collision, and the mountains were formed, okay. So that is the forces of compression, that when two plates are moving, they are moving towards each other, so this is a compression and you will have a folded mountain. This is a very basic example. Then you have forces of tension, where something is already together but there are forces which are causing them to move apart. So even during these kind of forces, you can have mountains, but they are called faulted mountains or fault mountains. We will see the examples of these, good examples of these, in coming lectures, when we will move towards plate tectonics and kind of different features formed due to these plate tectonics. Yes, Kuldeep, San Andreas is it's formed due to the transform motion. So there are two plates, okay, so they are moving past each other. They are neither colliding, they are neither going away from each other. So due to this movement, the material that is present at the margins, okay, they can kind of form an uplift. So that again comes under orogenic, but it is a transform fault, it's a transform plate boundary. We will learn about this. I will show you a diagram also where this is shown. San Andreas is another good example of orogenic and mountain building geomorphic processes. So then you have exogenic processes, where the influence, the factors, the agents that are causing these processes are acting on the earth's surface. Okay, so you have weathering, and you have erosion, and you have deposition. Okay, so weathering, you can have physical, chemical, biological. Physical weathering is, as we know that wind kind of erodes rocks, the weathering, sorry, we are talking about weathering. So one of the best examples of weathering is when a rock kind of disintegrates, okay. It is disintegrating because maybe there is effect of wind or water or say waves, okay. So weathering is the disintegration of a big rock unit. So the physical means that either wind or air or glacier or waves, they are acting on it. Chemical means the presence of some chemical acids or chemical precipitation, okay. So these are going to cause the weathering. Then you have biological, that means maybe there are any earthworms or some other kind of creatures that are causing the weathering or disintegration of a rock. Erosion is when some materials are kind of transported from one place to the other, okay. So running water can cause erosion, your groundwater can cause erosion, glaciers cause erosion when they are moving down the slope. You have waves and currents, they are they transport rock fragments or rock boulders from one place to the other. Wind carries sand from one place to the other, okay. So these are kinds of the erosion usually means the transfer of material from one place to the other. Now deposition happens on the other end of the erosion, okay. So with erosion, the material is getting transported, then it has to get deposited somewhere, right. So deposition is also one of the processes by which a landform can be formed. One very good example would be your deltas. Deltas are formed due to depositional action of the rivers and the streams that are and the tributaries that are flowing towards your ocean or sea, okay. So again, deposition can happen with running water, that is the rivers, then your groundwater, glaciers. We will learn about moraines, that is one of the depositional features of glaciers. you have waves and currents, and then also again we have winds. Okay, so this in short will tell you what are the different kinds of processes that are forming the geomorphological landforms. Okay, and the kind of driving forces and also the agents that are causing these geomorphological processes. This is in a nutshell, okay, the different kinds of aspects that we will learn when we are talking about geomorphology. So now in the this slide we learnt about all the natural processes. Okay, these processes or these kind of factors that I have explained, these are natural. Okay, you are talking about the natural agents, we are talking about the natural processes that are happening on and within the earth. Okay, so this will only deal with that. Now when we come describe chemical weathering again. Okay, so chemical weathering, one of the examples I can give you is the karst topography. Okay, what is the karst landform, karst topography? Suppose there is a huge area which is only made up of limestone. Okay, limestone is a rock and the essential chemical composition of it is your calcium carbonate. Okay, so calcium carbonate, we know that any kind of acid when acting on say carbonate material, it will dissolve into an acid. Okay, and it will start dissolving this calcium carbonate. So chemical is that either you will have these actions of acid. So when there is a calcium carbonate rock and the water is trickling down to these rocks, okay, this calcium carbonate dissolves. Okay, it starts dissolving in that water, and because of that dissolution of that calcium carbonate, you will start finding that it starts weathering, like it starts disintegrating. Weathering is disintegration of anything. Okay, so because of the action of the water, the calcium carbonate is getting dissolved, and the huge massive rock of limestone, okay, it starts disintegrating. Yes, stalactites, stalagmites, pillars, sinkholes. Yes, exactly. So these are the examples of karst topography, karst geomorphological structure. Okay, this is a kind of a special, kind of geomorphological landform that we will learn, that even the content will be given on this, but that is the basic explanation. Okay. Okay, so that as I was saying, that we learned about the natural agents, natural processes, natural forces that are kind of forming these geomorphological landforms. Now there is a very important relation or very crucial relation between such natural processes and our influences, like our as in human influences, anthropogenic influences. Okay, one of the biggest or the most visible example is that with increasing population, okay, our demands are increasing. So when our demands are increasing, we will exploit the available resources. So we will exploit our water resources, we will exploit our geosphere resources, that is your minerals and your fuels, fossil fuels, coal. Okay, because of the over exploitation, the natural rate of change of the superficial landforms, that will be disturbed. Okay, as I spoke about it before also, the timeline of the changes that we see on the earth surfaces is very very large. Okay, they are slow processes, they are time taking processes, but because of our activities, these processes have kind of the rate of their say output has increased and input has decreased. The for an example, when you talk about exploitation of fossil fuels, okay, so we are removing fossil fuels. Fossil fuels have taken millions of years to form. Okay, the input that it received, okay, the huge amount of input that the fossil fuel reserved, have had received during that time, that is, kind of negligible right now. So if we keep on over exploiting our fossil fuel reserves, there is no more input coming in, okay, and it's going to get exhausted, okay. So this is what I mean, that there's a delicate balance that we need to keep when we are talking about earth processes and the human influences. For example, I've also mentioned, sometimes rivers and streams get dried up because we divert the water for irrigation purposes. Also, deforestation is going to cause a lot of soil erosion and obviously land degradation because of that. So, normally rivers and streams do change their course, okay, but that is a slow process. It does not happen suddenly. So, the entire area gets, accustomed to that change in the course of the river. But when we do it, it's sudden, okay, so the entire ecology, ecosystem of that area changes. Similarly, when we are talking about soil erosion, that's the same thing. It's a very sudden kind of a shift from the normal state to a very different state. So the landform changes also happen suddenly. So when the earth processes, okay, when they become hazardous to us, uh, probably they were always hazardous, but because our population was very low, there was no population at all when it happened, in early earth's past, okay. So they were not hazardous because there was not much impact on the life and the property as such, okay. So they were hazardous, but they were not that hazardous. But currently, in the current scenario, any kind of earth process is going to be hazardous to life and property. So that is why we call these as geohazards. Geo means earth, hazards means any thing that causes risk to life, okay. So you can have natural geohazards and you have anthropogenic, okay. Natural hazards, it is impossible to stop them or to prevent them, okay. All you can do is kind of form risk management plans and kind of reduce the destruction that can be caused due to the natural hazards, natural geohazards, okay. So very common examples, volcanic eruptions, earthquakes, you have cyclones, hurricanes, tornadoes, tsunami, landslides and sinkholes, okay. So these are natural processes. These are these processes are a way that the earth surface changes, okay. So you cannot stop them. They have been happening in the past too, but it's hazardous to us right now. So we have to consider, understand these processes, learn how to mitigate the hazard that is being created by them, okay. Then you have anthropogenic. Sea level change, it's a very broad kind of a aspect. Sea level change also happens due to both natural and anthropogenic. Why? Because of the global warming situation right now. So that is why we are considering it as anthropogenic. Then pollution, air pollution, water pollution, groundwater pollution. These hazards are obviously mostly man-made. Then damming of rivers obviously disrupts the ecosystem of the rivers. You have dam failures, you have heavy siltation that is caused due to the damming of the rivers, which has an effect on the dams itself. Then you have wildfires because of the rising temperatures, because of the global warming scenario. You have wildfires. So also wildfires are sometimes also caused due to man-made errors and kind of purposeful activities also. So that is why geomorphology also deals with understanding these geohazards, how we can try to prevent, not exactly prevent, but at least try to minimize the risks that are present due to such geohazards, okay. So I have given you the different processes that act on, that are causing these geomorphological landforms to change or to form. Okay. different forces that are acting. Then you have the different influences that are going to cause these earth processes. Now there are some very important factors that we need to consider when we are talking about or learning about earth processes. So the first one we have kind of dealt with, that is natural agents, that is wind, water, glaciers, waves. Okay. Then the next important factor is the elements that are constituting the earth's material. That means the minerals, rocks and sediments. Why are these important? Because each of the minerals or each of the rocks have different set of physical properties. Okay. So for example, as we spoke about karst topography. Okay. So I said we are having an area of limestone. Okay, so limestone as a rock is a very weak rock. Okay, it gets weathered very fast. Okay, so suppose you want to build a kind of a structure, you are obviously not going to choose a site which is abundant in such limestone rocks or calcium carbonate rocks, because we studied in geomorphology that such places are very much prone to weathering, very quick weathering, due to interaction with say water. Okay, so learning about the elements that are making up the earth and also understanding the the interaction between the different agents that are there and also such areas is going to help you in taking care of these issues when you are trying to construct something. Okay, then as kind of I hinted before, that we also have to consider the role of plate tectonics and structural features. Okay, geological structures that we call them. Okay, when we are considering or studying an area for any respect. So you have like three kind of plate boundaries: convergent, divergent, transform plate boundaries. Over here, as you can see this example, this is the example of San Andreas fault. Okay, convergent plate boundary would be a Mariana Trench, as you know. Okay, so Mariana Trench is one example of the convergent plate boundary. And then divergent plate boundary, as we know, the Atlantic mid ocean ridge. Okay, that is dividing the two plates. Okay, that is an example of divergent plate boundaries. Then below you can see some folding, faulting and shearing kind of these structures. These are called geological structures. Okay, so these also need to be understood to understand how certain places, how certain landforms will be formed in certain places. Okay, and as I was talking about the elements that are constituting the earth's material, so you have some minerals over here, you have some rocks over here, that is crystal quartz is a mineral, basalt is a rock. Okay, then you have granite, marble. Okay, so understanding where what rock is present, what mineral is present, you can kind of understand the weathering that will happen over there. You will kind of understand whether it's a suitable area for any purpose, for any construction purpose. Okay, so this is also considered and this is also needed to study when we are learning about geomorphology. Over here you can see some examples of landforms that are present. These are all aeolian landforms. Okay, uh, I'm pretty sure all of you all have heard about sand dunes. Sand dunes are formed due to the erosional process by wind. Okay, erosional and depositional. Okay, so they go hand in hand when they are forming dunes. We will learn about these when we are learning about aeolian geomorphology. Okay, this is just some example to for you to understand that these are the kind of these are the kind of landforms we are talking about when we are learning about geomorphology. Okay, so you have natural agents, you have the elements that are forming the earth, and also the processes of plate tectonics and the formation of geological structures. Okay, these three factors influence most of the earth surface processes. Okay, now we come to Earth's energy budget. Why do we need to understand this? As we have spoken before, that Earth is a system, okay, a closed system. When you talk about closed system, that's only the exchange of energy. Why do we need to know this energy exchange? Why do we need to study about it? Because any process, okay, any kind of a driving force for any of the natural processes, energy is required. Where are we getting this energy? Okay, uh, suppose we are talking about, you know, the melting of sea ice. Okay, when we are talking about melting of sea ice, obviously heat energy is going to be related. Okay, so where is this energy coming from? Obviously it's coming from the solar energy. Okay, for that we need to understand how Earth's energy budget is. Usually in like a steady state, in ideal condition, amount of inflow should be equal to the amount of outflow. Okay, then it's a steady state, it's a perpetually running system. Okay, so when we are considering about Earth's energy budget, we know there are like it's said that 342 watts of energy is received by 1 square meter of the Earth's surface. This is the average amount. Okay, now considering 342 watts, okay, per square meter as 100 units of energy. Okay, so we can calculate, okay, how much energy is being received by the Earth's surface, how much is being absorbed by the Earth's surface, how much is, excuse me, reflected back into the space or absorbed by different elements that are present on the Earth's surface. Okay, so when we learn about the energy interaction within the Earth system, we learn how certain kind, what processes get how much energy. Okay, so over here considering 100 units of incoming solar radiation, 30 are being scattered back, okay, by the atmosphere that is present around the earth's around the earth and also the earth's surface. From the 30 units that are being scattered back, you have 6 that are scattered by the air, water vapor and aerosols in the atmosphere. Then 20 units are being reflected back by the clouds that is present. Okay, 4 are reflected by the earth's surface back to the atmosphere. Okay, 30 units are scattered or reflected. Now the remaining 70 units that are reaching the earth's, you know, it is reaching the earth's atmosphere. Okay, so that is equivalent to 240 watts per square meter. These are units. I will there are few problems that I have put over here. Okay, so we will calculate these things. Okay, so now you have the atmosphere and clouds are absorbing 19 units. Okay, then 51 units are remaining from the 70 units that are in the earth's atmosphere. Okay, 51 units is being absorbed by the earth's surface. Okay, and most of these are shorter wavelength, like we can see these we can see these units of electromagnetic solar radiation that is reaching the earth, because it falls in the visible range and it is mostly utilized by the land, water, vegetation, living beings for that matter. Okay, then the 51 units that is reaching the earth's surface, okay, 23 units of it is used to evaporate the water. Okay, so energy, as we talked about in the hydrosphere, you have evaporation of water, so that energy is given by these 23 units. Okay, then you have 7 units which is conduction or convection. Okay, so the energy, the heat, or that is kind of circulating within the earth, between the earth's surface and the atmosphere, that is given by the 7 units. Then the remaining meter square per hour or per day, it's just it's not related to the time, it's related to just the unit area. So I'm guessing it's probably at a certain moment. Okay, at a certain time this much energy is being received. Okay, so you have 51 units, I explained this. Okay, and the remaining of these 51 units will be again emitted back from the earth's surface. Okay, that is called terrestrial radiation. So we are considering that only 21 units are like remaining out of the 51 units that is received, that is absorbed by the earth's surface. Okay, but actually it's 117 units. Okay, because uh, radiation probably is being absorbed in the day, but the ones that are emitted back, it can happen both day and night. Okay, so that is why it's more than the calculated units that are shown here. Okay, so considering these different kind of units, different kind of numbers, we can calculate the amount of radiation that is interacting with the earth's surface, with the atmosphere, and also with considering both surface and atmosphere. Okay, so I will just solve this. Okay, so suppose we are talking about the radiation balance for earth's surface. Okay, so when we were talking about the radiation, amount of radiation that is reaching the earth's surface. Okay, so you can see absorption of solar radiation, we talked about it, it was 51 units. Okay, it was 51 units. And you have absorption of infrared radiation from atmosphere. Okay, if you see in the previous slide, we have written this. Okay, we have seen that 96 units is emitted back from the atmosphere to the earth's surface. Okay, so that is 96 units. Fine. So the total units of energy that is gained by the earth's surface is going to be 147. Okay, then we move on to the energy loss that is happening from the earth's surface. Okay, so the heat loss by evaporation of water, we spoke about it, was 23 units. Okay, then heat loss by convection and conduction and convection, that we saw was 7 units. Okay, then you have infrared or terrestrial radiation that is emitted back to the space, it was 6 units. Okay, now we said that there was some amount of units, we talked that even though it seems like there are only 21 units that should be emitted back as terrestrial radiation, that was not the case. Okay, we saw there were 117, out of which we took out 6, that was the 6 units of infrared terrestrial radiation is being emitted back to space. So how much remains from that? That is 111. Okay, if you sum all these up, this again will give you 147. So ideally that is what we are seeing. Okay, that energy input and energy output is supposed to be balanced. So the total units of energy gained and the total of units of energy lost by the earth's surface will be in balance. Okay, next if we see the radiation balance for earth's atmosphere. Okay, absorption of solar radiation by atmosphere, okay, because of the presence of the greenhouse gases and clouds. Okay, so we saw that this was 19 units. Okay, then again absorption of infrared or terrestrial radiation by atmosphere. Okay, terrestrial radiation, first we talked about it, that was reflected back from the earth. Okay, now it is getting absorbed by the atmosphere, that is the energy that it is gaining from terrestrial radiation. So that was 111 units. Okay, then you have latent heat released by condensation of water vapor. We talked about the heat being absorbed due to to evaporate the water. Okay, so that was again 23 units. These units are similar, but the way they are acting, the way they are interacting with the earth's surface or the earth's atmosphere is different. Okay, so at some place some units are giving the energy, at some places the energy for certain process is being absorbed while it is being lost in the other system. Then we talked about sensible heat released by convection and conduction, that was 7 units. So this totals to 160 units. Okay. Then when we talk about the infrared radiation emitted to the earth, we talked about the energy that was absorbed by the earth's surface. Okay. So absorbed by earth's surface, emitted by the atmosphere. So that was 96 units. Okay. And then the infrared radiation emitted to space, back to space from the atmosphere, that is 64. Okay. Again when you total this, it's going to be 160. Again, the total units of energy gained and lost by the earth's atmosphere because of the incident solar radiation is again in balance. Okay. So this is how earth's energy budget works. Fine. Then suppose we consider both together, surface and atmosphere. Okay. Can anyone tell me how much would be the absorption of solar radiation at earth's surface? I mean, we just talked about it. If I go back to the slide, yes, right. So that will be 51 units. Okay. Then we spoke about absorption of solar radiation by atmosphere. Does anybody remember how much that was? So that was 19 units. Yes, yeah. Okay, so it was 19 units. So the total energy gained by both Earth's surface and atmosphere due to the incident solar radiation is going to be 70. Okay. Then we consider the infrared radiation emitted from Earth's surface to the space. Okay, so that was 6 units. Yes, 6 units. Then the rest of the infrared radiation that is emitted from Earth's atmosphere to space. Okay. Suppose I am giving you the condition that these two have to be balanced. So if they have to be balanced, that means that this also should be 70. So then how much would be the what number of units would be the infrared radiation that is emitted from Earth's atmosphere to space? Very quickly, just like calculate and give it to me. 70 minus 6. So that would be 64 units. Again you can see that both of them are in balance. So there is no annual net gain or loss of energy. Okay. That is why we say that the earth's average temperature should remain constant, because the amount of energy that is received by the earth's surface is the amount of energy that is being reflected back by the earth to the space. Okay. Now the entire situation of the global warming is happening because this balance is not maintained. It is being tipped to one of the extremes. Right now we are gaining a lot more energy than we can lose. Okay. That is causing the what we call the global warming scenario. Okay. One of the very easy ways to understand this is the positive feedback loop. Okay, that is occurring. So there is an increase in the output. Okay. How much ever we are kind of receiving, we are not being able to give it back. Okay. So there is an excess. So that is kind of a positive feedback. Okay. Negative feedback would be all the energy that is coming, nothing is being held back, everything is just given out. Okay. So this is why it is important for us to maintain this energy budget or energy balance that is forming the earth system. Okay. Now electromagnetic radiation, why do we need to know this is because some of the particles, or as we call, the greenhouse gases, as we see the greenhouse gases, okay, major uh, these are the major uh, elements, you can say, which are causing the greenhouse effect. Okay, because of the greenhouse effect, a lot more heat is being trapped between the earth's atmosphere and earth's surface, which is causing the gradual increase in the global temperatures, which is causing ice melting, glacier ice melting, which is causing the sea level changes, and which is hazardous to us. Sea level change or glacier ice melting are natural processes, but when these changes or these processes happen at a suddenly rapid rate, that is when it becomes a hazard to us. Okay, so we are trying to minimize the hazard or minimize the risk that these processes are going to pose for the life and property on the earth right now. Okay, so why is it important to know the electromagnetic radiation? Because greenhouse gases are responsible for radiating long wave radiations. Okay, so if there were, and long wave radiations are not easily reflected back. We'll see in the greenhouse effect in the next slide. Okay, and most of the energy that is given, that is circulating within the earth's surface and the atmosphere, is mostly visible light. Okay, but the visible light, sometimes when it is reflected back, or it the absorbed by the earth's surface, and then when it is being emitted back, it is emitted back as long wave radiations. Again, the long wave radiations are being trapped because of the greenhouse gases between the earth atmosphere and earth surface. So this is what we are talking about as the greenhouse effect. You can see that one is the long wavelength infrared light, two is the short wave, and three is the visible. Okay, so the long wavelength is not even, it is not entering the glass, the greenhouse. Okay, that is fine. It is being reflected back. Suppose your this is the atmosphere. So the long wave radiation at first is getting reflected back. Okay, that is not causing any harm to us. Now the short wavelength infrared light, okay, that is entering, that is entering, okay, that is being absorbed by the earth. Okay, after being absorbed by the earth, it will get emitted back into the earth's atmosphere as long wave radiations. Okay, sorry, in the previous slide, yes, sun radiates in all wavelengths, okay, but only certain wavelength range travels into the earth, okay, from the atmosphere. You can see this as an example. The long wavelength infrared light is not entering, okay, but your short wavelength and your visible light, okay, visible light, the section, that is entering into the earth's atmosphere, and it is getting absorbed, it is interacting with the earth's surface. In the previous slide I said that the visible light is getting emitted back as long wave radiation. I'm sorry, that is a short wavelength infrared light that is getting emitted back as long wave radiation. Now we saw that long wavelength radiation gets reflected back by the atmosphere. Okay, so since earth itself is emitting the long wavelength infrared radiation, it is not it is not traversing through the atmosphere. It is getting reflected back by the atmosphere towards the earth's surface again, or it is circulating in that region itself. So this is why the greenhouse gases are acting as the barrier, and they are not letting the long wave radiation get reflected back into the space. This is causing the entire global warming because of the greenhouse effect. You can see very easily that these are the paths that the different the radiations are taking. Okay, so this is a good example to understand the greenhouse effect and how even the greenhouse gases are, you know, kind of trapping the long wave radiations, which is increasing the earth's temperature on like a gradual scale right now. Another effect that is responsible, okay, for kind of increasing the temperatures, the global temperatures, and also affecting the geomorphological processes that are happening on the earth, that is a albedo effect. Albedo is the measure of how much how a surface can reflect light. Okay, because of this albedo effect, we can see some of the colors, you know, brighter than the other. So, all the Earth's surface have kind of a, you know, an albedo factor. So, snow has kind of the highest albedo. Okay, so the we consider it like in the ratio form. So, 1, that is the highest, is normally for snow. Then ocean water has typically low, and if you see bare sea ice, okay, why is sea ice lesser than snow? Because sea ice has a lot of other components in it. Sea ice, you will have ions like say sodium chloride. Okay, so if any impurities are present within the snow, it will you know, reduce the albedo of that ice. So, since snow has the highest albedo, okay, so it will reflect everything that is falling on it. Okay, so it will not trap any heat. It will not, it will not warm the entire place in that sense. But if your sea ice keeps melting, okay, if your sea ice is melting, the underlying surface is getting absorbed. Is getting exposed. Okay, so the solar energy, again the short wave radiation that is falling, that is getting absorbed by the earth, and it will again get emitted back as long wavelength. Okay, so reducing you know, the reduction of snow, the reduction of glacier ice as we talk about, is going to expose the surface, which will absorb more solar energy, which will again emit more long infrared waves, long wavelength radiation, that is again going to get trapped because of the presence of the greenhouse gases, and it is going to increase the global temperature, which again will cause increasing melting of the ice. So it's a cycle. So albedo effect, greenhouse effect, and also the earth's energy budget, all these are interacting together and it is forming this cycle, but this cycle is not balanced anymore. That is why we need to understand the interrelationship between these things and how it's affecting the natural earth processes. Okay, see the next thing, okay, that kind of affects the in the, you know, the kind of the seasonal changes that we see, season, climate, local weather, everything again affects your earth processes, the surface processes that are changing the landforms of the earth. Okay, in this diagram you can see that the earth's uh, orbital motion, or the orbit that it follows, is not a circle, it's an ellipse. Okay, so over here as you can see, there is a perihelion and there is an aphelion. Aphelion is the point that is farthest from the sun, where the earth is the farthest, and perihelion is where the earth is nearest to the sun. Okay, so right now these are the you know, days, the close to these dates earth reaches the perihelion and aphelion. Okay, and these this is the distance that it is at from the sun. Not a lot of difference between the two, but there is a difference, and even this minute distance is going to cause uh, is going to influence the weather and the, you know, the season that is happening on the earth. In this diagram you can see that, you know, you have the you know, this is the area where you have the solstice. Okay, solstice is when the hemispheres kind of, you know, experience the summer. Okay, in your summer solstice that happens in June. Okay, the northern hemisphere is experiencing summer, okay, and in the winter solstice that happens in December, your southern hemisphere is going to experience the summer, okay. Why is it so? Because the earth rotates at an axis which is tilted, okay. So it is 23.5 is the kind of the axial tilt that is there right now. Because of the tilted rotational axis, okay, and this elliptical motion, elliptical orbit that is followed by the earth around the sun, you have these seasonal changes, okay. Then you have equinox. Equinox means equal night, okay. So your day and night are of equal time, okay. The duration of both day and night on those days are going to be equal. So you have a spring equinox, okay. So that happens in March, and another equinox happens in the September. So that is autumn equinox, okay. So this is the influence of these kind of very factual, these are not controlled by us, okay. These are natural things. This is the natural motion of the earth, okay, the rotation, revolution, which is also governing the climate, the weather, the seasons, and that in turn is going to govern your geomorphological processes, okay. Your tidal effect is governed by the seasonal and the the moon, the motion of the moon around the sun, earth's rotation itself, okay. So tides again will cause weathering, erosion and deposition, okay. Between okay, what was the question? What's the difference between solstice and equinox? Solstice is what we consider where, in which hemisphere the sun is moving, okay. So when you have the summer solstice, we consider the solstice as per the seasons that are being seen in the northern hemisphere, okay. So when your axis, when it's turning, okay, suppose I think you will see the opposite of me, but over here if you can see, okay, summer solstice is when most of the northern hemisphere is going to experience summer, okay. Yeah, equinox, yes, exactly, Kuldeep, thank you. Equinox is uh, the the solstice is only the hemispherical seasonal changes, okay. So if most of the northern hemisphere is experiencing summer at that time, so on that date you have the summer solstice, okay. And then when you have most of the northern hemisphere kind of experiencing winter, it is winter solstice. Equinox is when the sun's position is right at the equator, okay. It's at the horizon, or what you call as the zenith, okay, as Kuldeep very nicely has written, when sun is overhead at equator, and solstice when the sun is in either in the northern or the southern hemisphere. So when the sun is at the equator, okay, so that means it's at normal to the equator, okay. So this entire half, okay, this half is going to experience the day and this half the night, okay. And because of the axial tilt and the position of the earth, the duration of the day and night is going to be equal on those days. That's why it is called equinox. Equi means equal, nox means night. So equal day and night. Is that clear, the difference between the solstice and equinox? Who asked the question? Pravesh. Is that clear now? Okay. Okay, so this, the summer, autumn, spring, winter, these are governed by the earth's orbital motion. Now when we talk about the seasonal, that is your yearly variation, but climate change, okay, it's a long overdue process. It takes much longer for climate to shift from one extreme to the other. Okay, so one of the very what to say, influences, okay, we can there was a scientist whose name was Milankovitch. He gave forward this this principle that uh, because of the earth's elliptical motion and because of the features of this elliptical motion, there is a kind of a cycle with which climates either get like repeated or they start ending a certain climate. Okay, what are these three factors? You have the eccentricity of the orbit, okay, you have the precision of the earth's rotation, the precisional the movement, and the axial tilt that the earth has, okay, the rotation axial tilt. Okay, so Milankovitch cycle talks about the effect of the amount of solar heat that is incident on the earth and the way it affects the climate patterns. Okay, so it's a cyclic process. The climatic patterns, they change over time. Yes, very good. I am happy that you all are going through the content. Yes, wobbling and precision. Okay, so when we talk about the factors, okay, that are kind of affecting these, so the one is eccentricity. Okay, the eccentricity, okay, that is the the distance it is from the sun. Okay, it can be narrow, it can be the ellipse, the or the elliptical orbit. Okay, it could be narrower, it could be broader. Okay, so this changes more or less in like 100,000 years. Okay, that is kind of the cycle that is being given by Milankovitch. Okay, then you have the axial tilt. Okay, you can see over here. Right now, the axial tilt is 23.5. Okay, currently. So the axial tilt kind of moves from 21.5 to 24.5. Okay, so this difference or this kind of kind of shift from one value to the other, that cycle happens 41,000 years. Okay, that cycle repeats. So when you consider the axial tilt, more the axial tilt, okay, the hemispheres are closer to the sun. Okay, so suppose right now it is like this. So this surface is not that close, but if the tilt increases, one of the hemisphere or both the hemispheres due to the rotation will be closer to the sun because of an increasing axial tilt. Okay, now precision is the the one is the it is rotating about the axis. Okay, then there is a precisional motion that happens about the axis or for the earth. Okay, now wobbling and precession, as we call it, they both happen due to the the gravitational attraction between the earth and the moon. Okay, there is a cycle of repetition for this too, so that is between 19 to 24,000 years. Okay, all these three factors, okay, they are responsible for the different glaciation and interglacial period that we see. Okay, glaciation is when there is when there's a drop in the temperature. Okay, the temperatures are lower and you have mostly ice covering the surface of the earth. Okay, interglaciation is the, yes, ice age is a glaciation period. Okay, when the ice age ends, so suppose your axial tilt has increased, so it is closer to the sun, so the temperature, the incident solar radiation is going to be more, the temperature is going to be increasing, so you have that interglaciation period. Okay, so people who are kind of not saying, like they are saying that global warming is a natural process, it's not due to the man made kind of rapid pollution or rapid population growth. Global warming is a natural process and it is happening due to the interaction, due to the changes that are being considered for the Milankovitch cycles. Okay, in the in the so the right hand side diagram, you can see that It's a representation of how it will look after 150,000 years from now, okay, and how it was 5,000 years ago from the Earth's orbital pattern today, okay. So you can get an idea about how these keep changing, okay, and but these changes are a very long term changes. In our life we are not going to see it right now, okay, but it is present, it is happening right now, okay, and it will keep changing in the coming future also. So now we come to one of the first systems that we already learned about the the kind of energy relations that we have with the earth, between earth and sun, okay. So now the first cycle, first system, first sphere that we are going to talk about is the hydrologic cycle, okay. That is the interaction between the earth and the water resources that are present on the earth, okay. So as we discussed before, so you will have precipitation, you will have surface flow, surface runoff, okay, then you have a collection in the ocean, then from here again there will be evaporation, then again it will be precipitated, so it's a cycle, okay. Out of these cycling water, okay, so we there is a term called residence time, okay. So residence time is the amount of water that is present in the reservoir, okay. uh, it's a ratio between the amount of water that is present in the reservoir by the rate of addition of that resource or the loss of that resource, okay. So suppose you consider the ocean, okay. So ocean has a very long, it's a very high residence time, okay, 4,000 years. Why? Because firstly the amount is high, okay, while the rate of addition is also high over there, okay, compared to the amount that is already present in the reservoir, that is very small, and also the rate of loss is very small, okay. That is why your residence time is high, okay. Now for groundwater, we are going to see in the upcoming slides, it ranges from 2 weeks to 10,000 years, okay, because it is because within the subsurface the groundwater can be seen at different depths, okay. Due to the depth, due to the amount of time that it takes to reach that depth, the residence time changes, okay. We as living beings, we have the smallest residence time of water within us, okay. These are some of the examples, and these are the residence times for those examples. Also we know that most of the water that is found on the earth's surface is actually residing in the ocean itself, okay, and very small percentage of it is even accessible for us for consumption. So that is why learning about the interaction of water resources or the hydrosphere with biosphere and the geosphere is very important for us to conserve water, and also try to understand how even slight changes or off, the balance being off is going to affect us, okay. So the two main parts, or the two main kind of concern for us when it comes to hydrological cycle is the surface water and the subsurface water. What is the surface water? Surface water is any kind of water resource that is existing on top of the earth's surface, okay. It can be in a flow, it can be stagnant, it can be recharged, okay. So that is surface water. Most of the surface water is found in a watershed area, okay. What is a watershed area? uh, JE Reader has kind of defined it as it is the land body, okay, which drains into a stream system. So the one portion of the land, okay, there is one stream that is active over there, okay. So that is the watershed area of that one single stream. There could be two stream systems side by side, but there will be a boundary between them. This boundary is called drainage divide. Over here also in this diagram you can see that this entire portion or this entire line that if we draw is the divide. Okay, so that means only one stream is active over there. The other streams, the smaller streams over there, are also flowing into that stream. Okay, so you have one term that is drainage divide, that is the boundary between two neighboring drainage basin or watershed area. Then you have drainage density. What is drainage density? That is the length of the stream divided by the uh, area of the drainage basin. Okay, so if you have more number of streams, okay, that is coming and contributing in the main stream, okay, and the area is also, you know, not that large, it is a moderate area, so you can say that the drainage density in more is more. But this can also happen that there are a lot of streams that are there, but the area of the drainage basin is large. Okay, so the drainage density might not be more. Okay, so it's a ratio. Then we come to your subsurface groundwater. Okay, how do you get water in the subsurface? Okay, there are layers, okay, within the earth's surface, but because of the nature of the material that is present, okay, suppose this area has your loose soil, sand, okay, so there are voids in between the sediments, the soil particles, the sand particles that are present on the top layer. Okay, and these are loose, these are not compacted. Okay, and also this is exposed to the air. Okay, so this area is called zone of aeration. So you will have water kind of trickling down from here. Okay, water trickling down and infiltrating the subsurface layers. And why is it called zone of aeration? Because you will have water as well as air in the pockets or the voids that are present here, and this is called zone of saturation. Okay, because this is where your water, the infiltrated water, is going to get saturated, and it is present in the subsurface layers. Yes, Pravesh, I will come to the artesian wells in the upcoming slide. Okay, so you have two properties of subsurface layers which is going to govern whether water is being stored or water is being or water can travel through a layer. Okay, so that you have the porosity and permeability. So porous means that it has void spaces, or that I said pockets in between the grains of say soil, sand, or any kind of rock that is present. And permeability is the amount of connectedness that the voids have, so that the water can travel through that layer. Okay, so this is what, why was it, the subsurface groundwater is present, because the water infiltrates the ground and it will percolate, it will go down and it will percolate in a layer which is porous as well as permeable. Okay, so you have maybe soil or sediments or rocks which have porosity and permeability in their physical properties, which is going to contain the water that is infiltrating down. Okay, so now it's just if we consider that all the water should be then just moving down, okay, there should there should not be any lateral movement, but that is not the case. There is also lateral movement of the groundwater. So what are the factors that are, you know, governing or controlling the movement of the groundwater? Is your topography, whether if it's elevated or it's a depression. Okay, then you have the soil and the rock type that is present in that area. Then you have the amount and intensity of precipitation. More the precipitation, more amount of water is going to infiltrate. Okay, provided that your soil and the rock type over there is both porous and permeable. Then the vegetation that is present, and also the land use. Okay, so it's if it's a degraded land, it's all, you know, compacted, and there is no way, there is no a lot of clay is present. Clay is an impermeable kind of sediment. So if suppose there's a lot of clay, there is impermeability, so the water cannot travel through clay. Okay, so all these factors are going to influence the rate of infiltration and the movement of water. You can see over here that in the upper surface the movement is going to take in between like days and years. Okay, so the upper level, the recharge and discharge of groundwater is very is comparatively rapid or faster than when you come at the this confined aquifer that is much deeper. Okay, the infiltration also has taken a long time, and it is the the discharge will also take a long time, because to reach at such depths to extract water is going to obviously take a lot of money, and it's mostly not possible if we are considering a much deeper wells. Okay, now we come to the types of aquifers, the kind of what to say, the layers, the subsurface layers that are capable of holding water, like the water can travel through them, or they are blocked, or the water is kind of blocked by certain layers. So you have aquifer. Aquifer is that rock type or that kind of geological feature which will hold the water. So it can store water. Okay, it is permeable, so the water can flow through the aquifer from one place to the other. Okay, and yield of water is that it can give you the water. Okay, so if you say drill a well and kind of extract water from the aquifer, you can get it. Then you have aquitard. Okay, over here you can see I this suppose this there's a thin layer of clay over there. Okay, sandy clay. Okay, there's a mixture of sand and clay. Suppose it's like mostly close to the surface maybe. Okay, so it can hold water, not a lot. The permeability is lower. Okay, since the permeability is lower, your yield of water is going to be less. Okay, then you have aquiclude. Okay, this is a layer that kind of separates your unconfined layer with a confined aquifer. Okay, aquifers can be two types, confined and unconfined. Unconfined is it's not blocked, or it's not there's no barrier on top of the aquifer. Confined is it is bound between two impermeable layers. It can be aquiclude or it can be aquifuge. Okay, it's mentioned over here. You can see aquiclude can store water, but it is impermeable. Okay, so it has porosity, but it has no permeability. So because it has no permeability, it you cannot extract water from these kind of layers. Okay, aquifuge, it has no porosity, no permeability. This will act as a bound for the confined aquifer. Okay, now when we were talking about artesian wells, okay, I think Pravesh asked this question, what is an artesian well? Artesian well is that well that goes all the way up to confined aquifer. Okay, now confined aquifer, as I said, that it is bound between two layers where impermeable layers, one aquiclude, one aquifuge. Okay, so the water in the confined aquifer is under pressure. Okay, so what happens when you pierce something which is under pressure? The water will start coming out of the well on its own. You don't need that pumping. Okay, that is why you say artesian well. Okay, so you don't need external pumping of the water from the artesian well. It is intersecting the confined aquifer. Okay, and the water itself is flowing up the well. Okay, that is one thing. The other aspect is cone of depression. I think it was there in this. Okay, this well is not an artesian well. Why? Because firstly you need to pump the water from this well. This well is not reaching the confined aquifer. Okay, so now the confined aquifers are usually much below the the normal water table of a region. Okay, but a well like this is going to only reach up to unconfined aquifer. Okay, and as the water is getting extracted, it will form a cone, that is the water table starts decreasing because of the pumping of the water. Okay, so this, the one that is mentioned here, this is not an artesian well, this is a normal well, And when a normal well is being used to take out water from an unconfined aquifer, you will form a cone of depression, and the water table slowly starts going down. Okay, but over here if you see, this could be an artesian well, this is an artesian well. Okay, the water flow is it's on its own because it's under pressure between two bounding layers. So this is an artesian well. Okay, is this clear now, Pravesh? Artesian well. Okay, good. So the that's why, you know, again when we say you know, groundwater is one of the agents that is going to you know, make up some geomorphic landforms. Okay, and the elements or the minerals and the rocks that are making up these aquifers is going to control the effect and the, you know, kind of flow, inflow and outflow of groundwater. Okay, then some tectonic processes can, you know, hinder or it can change the groundwater level or the water table, for example an earthquake. Okay, so we can say that again these factors is going to affect this system, the groundwater system, the surface water system, and in as a result it is going to form a different geomorphic landform. Okay, now this is an example of interaction between surface and groundwater. Okay, so groundwater essentially is responsible for recharging a surface water feature, maybe a stream. Okay, so there can be an influent stream and there can be an effluent stream. What is an influent stream? Okay, the stream is recharging the groundwater. Okay, it infiltrates the ground and recharges the groundwater. Okay, so the water table rises because the stream is recharging the groundwater. What is an effluent stream? It is the opposite. The groundwater is recharging the stream. Okay, and the water table slowly goes down because the water is being taken up by the surface stream, that is the effluent stream. Okay, then as we discussed before, you know, any kind of groundwater activity or surface water activity on a limestone rich area is going to, you know, cause caverns and sinkholes because of the dissolution of the calcium carbonate that is present in the limestone. Okay, this is again it's an example of the interaction between surface and groundwater. Okay, so now we learnt how water, while it's important for us, it is also going to, you know, affect the earth surface, the formation of the earth surfaces. Okay, you can see the surface water can erode, surface water can weather a rock, it will kind of you know, transfer sediments from one place to the other and it will deposit there, or in the example of the karst topography it will start causing chemical weathering. Okay, and it will form these weathering features. You can see over here, as before also I think Kuldeep had mentioned stalactites and stalagmites. Okay, so we see that surface water as well as subsurface water is going to act as an agent which is going to change the earth surface. Okay, so for today we have till here. If anybody has any questions in the content that I have explained today right now, you may ask. You can either type it out in the chat box or you can ask by unmuting yourself. Any other doubt, any other clarification regarding these live sessions, you can ask right now. Thank you so much, Kuldeep, for your very kind words and review. And I hope this is going to help you and you will participate just like you did today in the upcoming live sessions. This will be held every Friday and hopefully you will interact with me like you did today, and we can clear your doubts as well as people who kind of miss the lecture, who can see these lectures later. And okay. Any other query that you have, you can put it up in the discussion forum that is there. And in any case that I will with this these recorded lectures will be uploaded over there. Also, you will find other details, and the NPTEL team is going to give you the links for these recorded lectures. So it will take a few days, but I will try that every week before the deadline of your upcoming assignment I will be covering up those parts. Okay. So thank you so much for coming to this lecture and interacting
Mm.
with me. Okay. And please keep attending. It's 2 hours. It's mostly it will be a good summary for your entire week's content, and the matter that I will be giving here that will be present in the slides is going to help you in the assignments. And
Okay,
does
ma'am.
anybody have anything to say?
Yeah, yeah, ma'am. Yeah,
Okay.
ma'am.
Wait.
Can you hear
Maybe
me?
I can switch off the recording. I'll just switch off the recording. Then you can continue.